So, to draw our graph, I'm just going to label I should put here really number of spatulas of alkali, and up here we're going to measure the pH. And it's just a sketch, I'm not putting numbers on, I'm just trying to sketch this out. In the test you did, it wanted numbers, but I'm just going to use this as a sketch. So it's going to remain, because it starts off as the acid and we add the alkali, it's going to remain acidic for a long period of time. And then we get a very rapid, big increase in pH. So the pH up here is going to be strongly alkali, and then it levels off against this S shape is very characteristic of a neutralization reaction, adding an acid and alkali together, and we get a dramatic, as you can see, a dramatic shift in pH between the two. In terms of using universal indicator to monitor this, then what we'd have to do is test the pH at different points. And to understand what pH it is, you would compare the colour of universal indicator paper against the pH chart. So you have a little chart with all the colours on, and it tells you the pH for each colour of the indicator. Why would litmus be no good? Well, litmus is no good here because litmus, it goes red in acids, blue in alkalis. It doesn't actually tell you the pH, and that's what we've got to say here. We need to say that litmus will not tell you a value for pH. It just says if it's alkali or if it's acid. Ionic equation, remember neutralization is an acid. All acids contain hydrogen ions. With an alkali, so our alkalis contain hydroxide ions, and in simple terms, when they come together in the ionic equation, you make water, which is neutral, H2O. Explain what's going to happen to the hydrogen ion concentration if we change the pH. So, what we need to remember in this question here is a pH change of 1, which is what we've got. So pH change of 1. The core knowledge of this is that equals a hydrogen ion concentration change of the factor of 10. So it changes by 10 times. Because it's going from 2 to 3, so the pH is becoming less acidic, this would actually be a decrease of hydrogen ions by a factor of 10. Definition for weak acid, the final one. Weak acids, everyone got this right in the exam. They partially dissociate, partially ionize. So remember, let's give ourselves an example. Here is ethanoic acid, and it has a reversible symbol in the middle because some of the ethanoic acid will separate into the anion and the hydrogen ions, but it's only about 1 in 1,000. So in order to get 2 marks here, we need to show that bit of knowledge. So they partially dissociate, and this means that you will get fewer hydrogen ions are produced. You're not going to get as many hydrogen ions because the equilibrium actually sits on this side. It doesn't dissociate as much.